Okay, so this is the Chapter 1 notes for chemistry, and we're starting this on September 2nd, 2014. And we're going to talk about, first, the branches of chemistry. Okay, I lied. We're going to start off with what chemistry is, which makes more sense. And we've got our textbook definition there. Study of the composition, structure of matter, changes it undergoes, all that stuff. And that's fine, but the truth is that chemistry is happening all around you. It's kind of everything. It's been said that biology is the what, so I would add earth science to that. Biology and geology are descriptive. They describe what is around us. Chemistry is the how. So for every biological or geological process that you see going on around you, that is operating through some sort of chemical reaction. I mean, your body is a whole set of chemical reactions going on at every second. Then we go on to say that physics is the why, because there are actual physics principles that govern how and why those atoms behave in the way they do. We are not even going to brush that. That is way, way, way above the scope of this class. But chemistry is really how everything in the world works. It's how the things that you see happening are happening, which I find kind of cool. Okay, so in talking about the branches of chemistry, your book lists 6, and there are 3 that I am concerned that you know: organic, inorganic, and biochem. We're going to start off counterintuitively with the second one on the list, inorganic chemistry. That's what you're in. General chemistry at the high school level, at the college level, is inorganic. So inorganic chemistry is, well, the study of compounds that don't contain carbon, except sometimes we hit things that contain carbon. Humph. Non-carbon containing compounds here means things that are not carbon-based, that aren't centered around carbon. So there's a difference between coming across carbon every now and then, sort of accidentally, and doing nothing but carbon, carbon, carbon. Carbon, carbon, carbon. That's what organic chemistry is. So inorganic, things like sodium chloride, magnesium oxide, iron oxides, all of these things that are not carbon-based, those are the backbone of what we do in general chemistry. And it's the same thing if you go on to take college chemistry. Gen Chem is your inorganic. Now, to contrast that, let's talk about organic. So, well, first let's draw a picture. Okay, so sodium chloride, iron oxide, magnesium oxide. What else could we throw in there? We could throw in there potassium chloride. We could throw in any of those. Those are all inorganic. What else could we throw in? Okay, so those guys are all the province of inorganic chemistry. Organic chemistry, we say, is the study of carbon-containing compounds. And when we say carbon-containing here, we mean lots of carbon. We mean tons and tons and tons of carbon. We mean entire backbones made of carbon. So, how many of you have ever seen cooking oil? If you aren't raising your hand, you have homework tonight. Go look in the kitchen cabinets. Cooking oil is nothing more than a whole bunch of carbon atoms tied together in these crazy long chains. Gasoline, diesel fuel, heating oil, propane. If you've got propane tanks at home for either grilling or heating your house or for the stove. Butane. If you've ever seen a Bic lighter, any liquid fuel lighter, that's a butane lighter. So these are carbon-containing compounds. So when we're talking about carbon-containing compounds, we're talking about really centered on carbon. Carbon has this weird ability. Carbon can connect to 4 other things. Well, if you can connect to 4 other atoms, you can form these weird, cool lattices. You can do all kinds of crazy stuff. And carbon does all kinds of crazy stuff. Big chains, branches. Carbon even forms, and this is possibly carbon can form rings. Carbon can turn around and bite its own tail. So that's a cyclical carbon atom. And that's what organic chemistry does. Organic chemistry looks at all of these crazy carbon-containing compounds. Now, here's the other interesting part. Have you ever heard humans described as carbon-based life forms? You are all carbon-based life forms. If nobody has told you that up until now, I'd like to let you in on this big secret that you are carbon-containing life forms, carbon-based life forms. Because you're carbon-based life forms, that means that a lot of these organic compounds have some activity in your body. Caffeine is an organic molecule. It's a bunch of interlocking carbon rings. My favorite chemical. Many of the neurotransmitters, adrenaline, dopamine, serotonin. You may know somebody who is on serotonin uptake reuptake inhibitor. It's a class of antidepressives. Antidepressives. So, lots of classes of drugs are carbon-based because you're carbon-based. And so carbon-based chemicals tend to have activity in your body. That gets us to the next type of chemistry that I want you to be familiar with, biochem. So we can have carbon-based compounds that are existing out on their own. Gasoline, diesel, rubbing alcohol, methane. There's a lot of talk about methane in climate science because it's a potent greenhouse gas. Biochemistry is where we look at only those chemicals that have activity in living things and how those chemical processes in living things work. So a biochemist would be working on metabolism of certain kinds of foods, or there's a lot of biochemistry in neuroscience. I have a friend who teaches chemistry, and her master's degree is in neuroscience. And she said, chemistry was a pretty easy transition for me because there's so much chemistry in neuroscience. Because your brain is a bunch of neurons that are all reacting to neurotransmitter chemicals all day long. That's all you're doing. You're a big simmering pot of neurotransmitters. I know, isn't it a romantic notion of humanity? But that's what you are. So biochemistry, you're looking at only substances and chemical processes that are happening in living things. It's very specific to that. Most of the things that are looked at in biochemistry are organic chemicals, but we're only interested in them in the context of living things in biochem. Make sense? So physical, analytical, and theoretical chemistry, I'm not as concerned that you're familiar with those. I can tell you that physical chemistry goes a little bit beyond what they say here, study of properties and changes. Physical chemistry also at a higher level gets into the actual physics of why atoms move and behave the way they do. If you have to take a P-Chem class in college, bless your heart and kiss your hair goodbye. You're going to need a wig when you're done. I never had to do it, but I watched lots of people tear their hair out. Physical chemistry is fairly brutal. So analytical chemistry, we're talking about identification of novel substances. So if you followed any of the news of the Mars rovers, has anybody followed any of that? How amazing. We landed some little robots on the surface of another planet. They've been driving around for quite some time now, and one of their missions has been scooping up chunks of Martian soil and rocks. And there is a full analytical chemistry lab inside a robot the size of two of these lab tables. And they're doing microchemistry, and they're analyzing all the compounds that are found in the substrates in Martian rocks and soil and relaying that information to Earth. That's kind of mind-blowing to me. So that's analytical chemistry. We have a chunk of something, we don't know what it is. Let's compare it to known chemicals. That's analytical chemistry. Labs use a lot of analytical chemistry. If you have had any kind of blood work done, if you've ever been admitted to the hospital or had surgery or just had regular routine blood work as part of a physical, some of that would be analytical chemistry. Most of that's a little bit less complicated than that. And if you've ever watched any of the crime drama or medical drama shows and they say, CBC and full chem, that's going off to a lab where some analytical chemistry is being done on the blood, and they're looking for the presence of They have unknown substances in the blood. They're looking to compare those with known substances and identify them. And theoretical chemistry, that's the really highbrow stuff. That's where the PhDs are, for the most part, I think, or the Nobels, rather. It's a lot of modeling. It's a lot of heavy-duty math and probably less actual lab work. So it's theoretical. And there you're looking at sort of the things that underlie chemical behavior. So that's pretty sophisticated stuff. This will be very brief. You all took a quiz on this. It appears that you all know what's matter and what isn't. Light coming from the tubes in this room, not matter. The tubes themselves, matter. The atoms inside the tubes that are vibrating at a fast enough and high enough energy state to give off light, matter. A little whine that we hear from those tubes, not matter. So you I think, pretty well understand this. And mass. You took some mass readings in here in lab A1. You know that mass is just how much stuff there is. You can never, well, let's see. How can you change your weight? Several things. You can go to the moon. You can change your mass. Or you can change your, you can change your mass. If you have more or less mass, that changes your weight. Weight and mass are not the same thing. Weight is how attractive you are to the earth. The more attractive you are to the earth, the bigger your weight. That's the force of gravity acting on your mass. Your mass is just how much stuff you're made of. Okay? And, short of losing or gaining mass, your mass doesn't change. But your weight, so if you go to the moon, your mass doesn't change, your weight does. Okay. Atoms, they're the tiny little things that make up everything on the planet. And at one time we thought you couldn't break them up, and now we know you can, with great consequence. If we talk about elements, which we will talk about a whole lot as we go, the atom is the smallest chunk that maintains the properties of the element. So if we talk about gold is an element, aluminum is an element. Aluminum is not an elephant, though you could make an elephant out of aluminum. Oxygen is an element. One single atom of any of those things contains all the properties of that thing. So we'll keep that short because, again, I think you pretty well got that from the preliminary stuff, the quizzes and online videos. Okay, so we've got a nice thin sheet of aluminum atoms. There is only one kind of atom in that whole sheet. Okay? It's a an element is a pure substance. Aluminum is an element. It's only got one kind of atom. It's an aluminum atom. That whole sheet, we could unroll a sheet of aluminum foil a mile long. We're not going to find any other kinds of atoms. It's a pure thing. A compound has got more than one kind of atom in it. So this is my salt chunk. That's my salt. NaCl. Came from a mine underneath Lake Erie. There's my aluminum. And there are two kinds of atoms in there. There are sodium atoms and chloride atoms. There are no salt atoms. You can look as far as you want, as long as you want, over hill, over dale, through brook, through briar, whatever. You're not going to find a salt atom. You're not going to find a water atom. What kind of atoms do we have in water? Hydrogen and oxygen, yeah. We often refer to water as our Mickey Mouse because we have our big old oxygen with two little hydrogen ears. Okay? So we're not going to find a water atom. It's a compound. They're bonded chemically. You can't physically separate the chlorine and the sodium from one another in this salt. You can't physically separate the hydrogen and the oxygen in water. You have to do so chemically. You have to create a chemical reaction. And we can do that. And actually, we'll split water in here a couple times this year. It's really easy. 9-volt battery and a couple of wires. You can generate all the hydrogen you want at home. Unfortunately, you're expending more energy to generate the hydrogen than is contained in the hydrogen, so don't think that you've answered the world's energy crisis. But that's a whole other story. So elements versus compounds. Okay, we're going to talk about a couple different kinds of properties. We have two classes of comparison for properties. The first is extensive intensive, and this is pretty basic. We're not going to stress this a lot. Extensive properties depend on how much stuff you have. So mass, length, volume, the amount of energy something has. 1 liter of gasoline has less energy than 100 liters of gasoline. Pretty obvious, right? That means it's an extensive property. Intensive properties are the same no matter how much stuff you have. So gasoline has a point of vaporization. Gasoline vaporizes pretty easily. If you've ever pumped your own gas and you've gotten fumes, that's because that liquid is very volatile. It readily converts into a gas. The temperature and pressure at which that happens is independent of how much gasoline you have. The temperature and pressure at which gasoline will go from being a liquid to a vapor doesn't matter if you've got 1 liter, 100, 1,000,000. It's the same. How conductive something is. Same thing. Doesn't matter if you've got an atom, a single atom of it, or a mole of atoms of it. We'll talk about moles later. Melting point, boiling point, density. The density of a lump of aluminum is the same if you have a gram of it or a kilogram of it. The density doesn't change. So that's extensive, intensive. Okay, so this is much more important for our purposes. Physical versus chemical properties. And physical properties can be observed without changing the identity of the substance. The classic one that used to show up on, I think it used to show up on the OGT as a physical science related question. Which of the following is a chemical change? And one of them was, something melting, like steel, iron melting. Now, when you melt a lump of steel, the molten puddle of hot metal that you get, is it still steel? Yeah. I should be saying iron, sorry. Steel's a different thing altogether. So if we take a chunk of pure iron and we melt it, is it still iron? Yes. Then melting point is a physical property. The question to ask yourself always with physical and chemical is, if we see that happen, so if it's freezing point, if it freezes, is it the same stuff afterwards? Is it the same atoms of the same stuff? If the answer is yes, then that's a physical property. With chemical properties, when we observe the property, it's a different thing after we have observed it. So if we get something to burst into flame, anybody here ever seen a lump of magnesium? Okay, where'd you see it, James?
It's not a lump, but I saw like sharks and stuff because in the place where I work, it does engine work.
Ah! And there are magnesium crankcases out there. VWs have magnesium crankcases. Panios? Anyway, okay, we'll talk later. Where'd you see magnesium?
We were burning some helium.
Okay, so yeah, you may have seen strips of magnesium in a lab. Also, if you have ever installed or uninstalled a hot water heater, typically hot water heaters have a magnesium rod that's screwed in, and it's called a sacrificial anode, and it reacts with other ions in the water, and it means that the water coming out of your hot faucets isn't black and interesting looking. So those magnesium rods, magnesium's interesting. So magnesium burns, and it burns hot, and it burns bright. And yes, throwing magnesium crankcases on a fire is a guaranteed way to light up the night and create a beacon that can be seen probably from the moon. But it's one of those metals that you can melt it. You can melt magnesium. If you melt magnesium and you go from having solid magnesium to a puddle of molten magnesium, that's a physical property, physical change. If you heat magnesium up in the presence of oxygen, though, magnesium is just as likely to burn. And when it burns, when you're done, you no longer have magnesium. So that point of flammability, that flammability, is a chemical property.